Dr. Gray.
This is Dr. Casanova.
Dr. Casanova. He seems like he'd be a chill instructor.
He
Just seems like a super nice guy.
is.
The name itself.
The name, yeah.
He studies stars.
How smooth can you be?
He likes the stars.
Yeah, he does. That's a cool profession. I wanted to be an astronomer at one point in my life. Anybody know Carl Sagan? You guys know Carl Sagan? He's not with us anymore. You kind of know who I'm talking about? Yeah. They ran this show called Cosmos, and when I was like 14, he was my idol. He just was like this 40-year-old dude who wore turtlenecks and jackets, and I like dressed like him. Wanted to be an astronomer and study with him, but then I don't know. I don't think I could be up that late. Maybe astronomers don't have to be up late anymore.
I'll have to look at the night sky.
To look at the night sky. Yeah, I'd be like a radio astronomer, right? Just check out black holes and shit from a million miles away.
You could just do theoretical astronomy. And
That's
just
true.
Do it all on paper.
That is true. That sounds very mathy.
Isn't that like kind of your thing?
It is kind of my thing, yeah. Corrections, let's make them due on Monday. So start a class on Monday, is that okay? Everybody's upset about that. Were you upset about that?
What?
I thought I heard you say, what? Or something.
No, I'm just
Okay,
I'm
cool. That's good. Cause I kind of wanted to have a Zoom class on Friday, if that's cool. Is that okay with everybody? We do that? Anybody upset about that? Friday? What's that? You're crying? No, on Friday. Oh God, okay, I knew you were joking if you said you were crying anyway. Yeah, on Friday, yes sir. Yeah. Okay with you? Everybody? Cool. Okay, awesome. My wife's out of town, and I've got a meeting that's already by Zoom, and I just don't want to go out of my house at all.
That's fair.
Is that fair? Yeah, thanks. Thank you, I appreciate you. So let's put that up here, Friday, Zoom class, and I'll record it like I always do, so if you can't make it, or you just freaking hate Zoom. Some people hate Zoom. You hate Zoom? Do you?
But I'll make an exception.
It's not, it's not an all the time kind of thing. And I generally keep my Zoom classes pretty lively.
Oh.
I try to, as lively as it can be. So I'll give it a shot.
I mean, it's also on its 50-minute day. Like
It's the 50-minute day, yeah, exactly. And we'll make sure it's 50 minutes.
49.
49, how 48 minute?
Yeah, 48 minutes.
48 minute class. I love it.
Twitch instead of Zoom. Thanks for
It
the
starts live streaming.
$20
Thanks for the sub. Hilarious.
Oh, that is good. Should we start doing this on like Twitch?
Yes,
Or something?
we should.
That'd be so
We
good. I'll
gotta
get the headset. I'll be
I'm
like
kidding.
playing
No,
something.
You can even
That's
get the
crazy.
desk mic too that comes out.
Yeah,
so
I
it, like,
do.
sits in
I
front of your
do.
face.
How's so we have a web work. Anybody started on that?
Alright.
Okay, gotcha. That's cool. Start on it if we need more time. I don't know when it's due.
Sunday's Sunday.
Sunday's perfect. We're
Yeah,
good.
it's
Don't even.
And I'm kind of feeling like Friday Zoom is going to be, maybe we all just get together and work, and I like help you get that assignment done. That would be cool. Yeah? Awesome. Oh man.
Like you're saying, we're just gonna like work every problem on the web work.
Well,
What
I
if you
mean,
need help?
more,
It's a work day.
It's yeah. And maybe so I wanna actually pose a question to you. So last time we did area between two curves. Let's just do this really quick and make a fancier one. So there's that double helix. I know, God, it's easy to get confused. And there's g of x. So if I would ask you to find the area bounded between these curves, can somebody tell me what I need to do?
You need to find the bounds between the
Bounds.
shaded area.
Yeah, so step one is find the intersections, right? And so I'm going to set f of x equal to g of x. Definitely get a picture out with Desmos or whatever. So we'll find these points A, B, and and C. So cool, we've got those. So X equals A, B, C. Somebody tell us what's next.
You need to find the area from A to B.
Cool. Yeah, how do we roll this? So area over your range. What's the thing I have to watch for?
You have to watch for the top and bottom functions.
Top and bottom, right? Yeah, because it's always going to be top minus bottom. I want you to like to start getting used to this idea. We're always going to do, when we're doing areas, top minus bottom, right minus left. So you know, the world's very right-hand biased in many ways. I don't know if that's because right-handed people made the world, a lot of it. I mean, and the left-handed people have amazing skills, but I feel like there's more righties, right? So what am I going to put in here? And is it going to be A to B, or do I want, yeah, A to B?
It's going to be f of x minus g of x.
It isn't. Let's be careful.
Isn't it
Who's
g
on
of
top?
x?
Oh, g of x.
Yeah. So just be real careful with what's on top, and then what? What else?
And then it's the integral between, is it A and B? Or sorry, A and C.
B to C.
B to C, yeah. This little window right here, and now what do I have?
So the same.
F of x minus g of x.
Now we got a different top, yeah. So just be,
Oh.
yeah, I just wanted to kind of get that in there, because I think there's a problem kind of like this on the web work. You'll have to do this one, so just be careful.
I see.
That's all, good.
Wait. I have a question.
Yes, sir.
So, yes, let's take like, so one day in class we did an example similar to where we had two bounded areas.
Yeah.
Where the functions like flipped, but we like took, never mind, I'm right.
Cool, no, that's great,
Yeah.
you're getting yourself oriented,
Mhm.
outstanding. So let's look at a slightly more interesting problem. Not that that's not interesting, but what if I had f of x is 1 over x, and I wanted to find the area underneath that curve from 1 all the way to the right.
Would it have to be like a limit?
Yeah, we're gonna need, yeah, it's calculus, right? We're gonna definitely need some limits on this.
But like, it's like something going to infinity.
It is, yeah, exactly. So we're gonna bring in our whole notion of limits at infinity to do this, but we're gonna actually approach it like this first. So if I want, go ahead, oh, was that a question?
No, I'm just, nothing.
You're good?
Yeah.
Okay, awesome, okay, cool. No, you're excited, man, I'm excited too. Who wouldn't be excited at this? So here's our basic plan. We're going to actually just find the area of a finite region. So we're gonna make a point out here, B, and here's 1, and here's the curve, and that curve is 1 over x. So the first thing we do is we actually create an arbitrary definite integral from 1 to b, and then I've got 1 over x dx, and then I'm going to work that through. And then I'm going to do what Alexander was suggesting and take the limit as b goes to infinity. So we're going to make a formula and then take that limit. And we're probably going to have to review how to do limits at infinity. I know that. I'm prepared for that. Yeah, all that stuff. Yeah, there's like a lot of little tweaks in there. So maybe you guys can help me. What's the antiderivative of 1 over x? I hope to God we know
Natural
this.
log of x.
Is natural log of x, yay. So this is natural log of x from 1 to b. Then I plug in the b and the 1. Keep this limit, carry this along. Natural log of b. It looks like b is a positive number. It's bigger than 1, so I don't need absolute value. And then natural log of 1. Now, Alexander, what is the natural log of 1?
0.
Yeah. Solid. Thank you. All right, so we've got limit as b goes to infinity of the natural log of b. How do we do that? How do we even think about it?
Gosh, no, I literally remember how to do this.
I'm gonna give y'all a second. I'm gonna go pee. You're welcome, recording. I'll be right back. So you figure, what's the limit there? Maybe get a graph out.
That's it.
Huh.
That's what we tell school. Because if you were to solve that one, it would be infinity over infinity. Just like 1 to 1, or 0 over 0. This is this is Calc 1 notes, by the way, that's why you don't recognize it.
No idea.
I just remember from this class.
Mhm.
Okay, that's it, that's all there is. Yeah. I don't know if this is exactly, what, I know we get this, wait, where did it show? Yes, the infinity, if you think it's gonna be able to do these, I don't know, if it's gonna be able to figure out this is different class, so it's gonna be more, I think it's gonna fall under, talk about this. Let's find out,
Oh, so let's find out.
Yeah.
What do we got? Somebody tell me, what's the limit?
I don't know the limit.
Kelvin's writing code to figure this
Is
out
it
right
like
now.
No.
No. No, I'm just kidding anyway.
It's a rule.
But you could, I would, yeah. What's this?
Rule.
Well, let's not do it with rules. Let's just do it with like thinking about what natural log looks like and so forth. Because there's no specific, there might be a rule. You might have learned a rule about it. What does a natural log graph look like?
Like that.
Like that, exactly. You know it, man. And then out here at 1, it spits out an E, right? We've got some good points on it, yeah. What is happening to the output as I move to the right?
It's increasing.
It's increasing. What do you say then the limit is?
It's positive. Increasing.
It is positive.
Increasing towards infinity.
Increasing toward infinity, so we
Positive
just say
infinity?
in positive infinity. We got there. Yeah, positive infinity. So infinity, so I want you to maybe change your conception of infinity. And it's actually a lot like what Alexander was saying. Infinity's not a place we can get to, it's just an aspiration. So this is just saying that the bigger B gets, the bigger the output gets. And this specifically tells me, hey, you tell me how big you want the output. You say, oh, I bet you can't get it bigger than M. And I say, well, you're wrong, because all I have to do is move out this far and it's now bigger than M. And you say, well, wait a minute, I'm at 2M. Oh, now you'll never do it. And then you just move down a little further and you eventually produce a place where it is that big. So to say this is to say this can get as big as we want by simply moving B to the right as much as we need to. So that's an easy one. Let's put up a couple. It's not easy. It's easy after you see the picture, right? And you talk it through. Let's write up a couple limits that we might need to understand. So let's say I've just got, and we'll do them in B's. Why not? What's that limit?
Infinity. Something over infinity.
Something over infinity,
Infinity
and
over
it's specifically 1, right?
Yeah.
Yeah. So that's right. That's a good way to think of it.
Natural log. X. Integrated.
No calculus. I mean, no derivatives or integrals or anything. Top is fixed. Top is stuck at 1. What's happening to the bottom?
Growing.
Growing.
Bigger.
And so what's happening to the ratio of something fixed over something
It's
expanded?
getting bigger.
Yeah,
It's
just
getting smaller. Yeah, yeah.
But if you have a 1 to 100 versus a 1 to 50, how is that smaller?
Cause you
You're
start
going the wrong direction
Yeah.
in your brain. So if I have 1 over 100,
Yeah.
1 over 50 would actually be.
Oh, because the fraction. Yeah.
Yeah. So as the denominator gets bigger, the fraction gets smaller, and we just say what? 0, because you tell me how close you want this to be to 0, and I'll tell you an X value that gets that close. That's what this means. Yes, sir? Yeah, let's talk. It's probably been a while since you've even seen limits. It's probably been a long while, and it's not a thing you're missing.
For something like this, don't you write like less than 1, greater than 0?
So you're thinking of the squeeze theorem, I think.
Okay.
And that could come into play in a situation like this. Let me, do you buy this?
Hmm?
Do you believe this?
Yes.
Okay, cool. Now buy it. Like, show me the money. Show me the money. So if someone said, what is this? Here's what I think you're thinking of, Jose. If we have this, and then you sketch out the graph of that, it actually is 1 at 0, believe it or not, or your approach is 1. So the graph looks like that. And so what you're thinking of, this is always less than 1 over x, because sine is always less than 1, or less than or equal to. And this is greater than or equal to negative 1 over x, because sine is always greater than or equal to negative. Is that making sense?
Mm-hmm.
I think this is what you're thinking.
Yeah.
And then I take the limits on each side. This goes to 0, this goes to 0, so it squeezes. You're thinking of the squeeze theorem. So I know that this goes to 0 as x goes to infinity.
Yeah.
Yeah,
That's what I was thinking.
I thought so, yeah. Do we have to, what?
Do we get to learn that?
We just did.
Well,
No, I'm just kidding. What do you mean? So tell me more.
is that a topic that you talk about?
No, probably not. Not much.
So it's not useful.
No, I think it answered Jose's question. It's incredibly useful.
It's not useful enough for you to teach, though.
Well, if you want, we could send you back to Calc 1 where I would teach that.
Did you learn that in Calc 1?
No. You didn't?
No.
I did, yeah.
You did?
But I didn't take it here.
Oh. Yeah, you guys,
We all took Calc 1. I
Yeah.
got all
You
of
don't
us.
remember
Was
this
they
in
the
Calc
only
1?
one who didn't take Calc 1?
Okay.
I think so, maybe.
I took it
What
with
was
the
it?
Greek.
L'Hopital's rule?
Yes,
Oh.
that's the one that, yes.
Oh.
Yes,
You did this. Yeah.
yes.
Yeah.
That's nice.
That's what it was.
Did you take a derivative for that?
I thought you took the derivative of the top
Oh.
and the derivative in the bottom.
So
It was
let's talk about L'Hopital's rule. So if I have a limit, no matter where it's going, let's just say to A,
F
and
of
it's
x over g of x.
f of x over g of x.
F prime of x over g prime of x.
And well, it depends. I can't always use it. If
If it's 0 over 0.
it's 0 over 0
Infinity
or
or infinity.
yeah, there you go. Then, only then, can I say this is the limit as x goes to f derivative over derivative. Yeah, so that's L'Hopital's rule. And we might need that. We might need that. But it doesn't apply here because the top is 1.
This is where
Mhm.
I thought you were going with that limit.
Oh, gotcha. Gotcha. Let's make this a little bit bigger. Or more encompassing. What if I have 1 over x to the alpha, and alpha is a positive number? What is that limit?
1. Something bigger than 0.
So let's say, for example, like alpha is, alpha could be 2, right? Then I have 1 over x squared. Let's think this through. As x gets bigger, what happens to the denominator? The denominator
It gets bigger.
bigger,
Yeah.
but the whole fraction gets smaller.
Yeah.
Yeah? So I think we're thinking the same stuff, we're just not all talking about it. So this would go to 0 as x becomes bigger. And all that's saying is this shrinks as x grows. So this is going to be the same thing. In fact, this is a good rule to remember. No matter what that power is, even if I had a square root on there, it's not going down as fast, but it's still going down. So this is going to equal 0 when alpha is a positive number. So we're going to need these fun facts along the way. Let me ask you another one. This one's not a general rule, but since we're all like hopped up on L'Hopital's rule, what if I had 3x squared minus 2 over 5x squared plus 3x plus 1?
You'd have to,
3/5.
so, okay, you put,
What's up?
3/5.
How'd you get that?
Because the exponents are the same, you divide the coefficients. But
Oh, yes.
that's the rule, I don't know why.
That's some good shit. That's okay. So Kellen is using this rule that if you have a ratio of polynomials of the same degree, the limit is the ratio of the leading coefficients. But I want to use this stuff up here to show you. And then we'll use L'Hopital's rule to show you. So just really quick, notice I can rewrite this as limit, this should say x, by the way, as x goes to infinity. Divide the top by x squared and divide the bottom by x squared. And let me just make sure that this board is so shitty. Make sure that looks okay to you. So I just divided top and bottom by x squared. You guys cool with that?
except the coefficients.
Say that again?
Oh, not dividing the coefficient,
Uh,
obviously.
what the fuck is this? This should just say, oh, it's hard, it's because it's,
No,
no, it was my, I saw stuff from residue.
I was just saying, you said you divided the top and bottom by x squared, but you don't divide 3 to 5 by x squared.
But I did.
Yeah,
Oh,
because
you
you
just,
don't have.
you just didn't, okay, yeah, you're.
Does that make sense?
Yeah, I just didn't see the step.
Okay, yeah, this is good. Is we cool with this? Yeah. Jose?
That's it,
Cool?
yeah.
Okay, cool. So, now let's go in here. Where does this go? What happens to 2 over x squared as x blows up?
0.
There you go. What happens to that?
0. 0.
So there's one way to see it, just using these rules up here. Goes to 3/5. Is that, yeah? Does that kind of help? So then we can think this through, right? Just using these very basic rules. And that idea that x is getting bigger, what's happening to the fraction? Let's do it with L'Hopital's rule. Quickly, let me try to get a better pen because the board is so putrid. Ooh. All right, so where's the top going as x goes to infinity?
3.
Just the top. No, it's not going to 3. So think x is becoming a big number. Then I'm squaring
To
that
one.
number. Not 1.
Wait, what?
What is the limit as x goes to infinity of 3x squared minus 2? What does the graph look like? Y equals that. What's y equals that? What shape is it?
It's a parabola.
Starts with a P. Yeah, parabola.
Yeah.
Is it open up or down?
Yeah, it's, wait, yeah,
Opens up.
it's under minus
And we
one.
could, if we needed to get points, we could get that picture.
Yeah.
What happens to the y as x gets bigger? As you move out this way, what's happening, if you're on the graph and you're moving to the right, what's happening to your elevation?
Y is getting bigger.
It's getting bigger. Does it ever slow down?
No.
Just think. I mean, and with these limits, you can literally plug in a number. Plug in 1,000. When x is 1,000, this is 3 million minus 2. When x is 1,000,000, this is so freaking big I don't even know the name of it. It's 1,000,000 squared times 3 minus 2. It gets bigger. So you can plug in these numbers and get a sense of it, or look at the graph, or just know that any polynomial, this might not be a bad thing to know, that the limit of any polynomial is going to be plus or minus infinity. It depends on if you have a negative or a positive out front. Depends on if the thing opens up or down as you move out this way. Is this making sense, the things I'm saying?
Yeah.
Okay. All right, good. That's good. I just need some encouragement.
So then,
Yeah.
does the denominator also go to infinity?
Yes, thank you. Beautiful. So the bottom also blows up because that's just a parabola.
Yeah.
And this quantity's getting bigger. It doesn't matter, even if I had had this in there, the x squared is dominant. right? When x is 1,000, this is 5 million, but this is only 3,000. So the front is blowing up so much bigger that this is going to go to infinity over infinity. And now I can use L'Hopital. So let's use L'Hopital's rule. We've got it right here. So this thing, only because it's in that form, this is called an indefinite form. Because it can actually end up being anything we don't know. So I'm going to take the derivative of the top, which is what? 6x. Cool. How about bottom?
5x minus 10x minus 3.
10x minus 3. Awesome. What's that limit? What's the top doing?
Getting big.
Getting big. Infinity.
Bottom getting big also.
Infinity over infinity.
Yeah.
What could I do?
Find
I can
the
L'Hopital that shit,
Yeah.
right? So I L'Hopital again, put a little L apostrophe H. This is limit as x goes to infinity of 6 over 10. Beautiful. Hey, that looks familiar. That's called 3/5, right?
And then, well, no, it's the derivative of 3x squared minus 2 is.
Well, yeah.
Are you good, Jose?
Yeah.
Okay. So just a little bit of review. So at some point in your life, you saw this stuff, and you probably did a bunch with it. Whether or not that's stuck, it's all good. We're coming back to it. It's on.
I got this one now. L'Hopital.
Good. Yes, sir.
So you just keep like getting the derivative until you get a fraction?
Yeah, until it's no longer an infinity over infinity or 0 over
Right.
0. Yeah,
Okay.
yeah.
If you were to attack that, like before you did the derivative of 6x and 10x stuff, if you were to also, okay, so I'm a little lost.
Yeah, well,
because
so
I
ask
don't
your
remember,
question.
I just don't remember doing, like, finding the derivative and then finding the derivative again. It was just the derivative of what was presented.
That might be.
And so, but no, it's not, because you took the derivative of that and then took the derivative of that. to
I
get
mean,
to
I guess I was saying it might be, I don't know what happened
Oh,
when you took
oh.
it. Yeah.
Well, okay, but that's fine, that's not what I'm asking,
Yeah, yeah.
can you just explain what that is? Like, I don't, okay,
Okay, well,
never mind. We're good.
no. So, we had this problem.
Yeah,
We're trying to
why
figure it
can't you
out.
take that derivative and say L'Hopital's and then call it good?
Well, because the derivative of that is this, right?
Yeah.
And now, what's happening there? The top is going to infinity and the bottom's going to infinity.
Yeah,
So I don't know what that's.
but it isn't also going to infinity in that function?
Yes.
So then why can't we just say it's that function, the derivative of
No,
that?
Because we're looking for a number.
We're trying to
We're
stop.
trying to find a number.
Yeah.
Yeah, we're trying to find. If you graph this out, can you bring up Desmos really quick? Please. I'm not trying to be bossy.
No, not at all. I'm good with this.
Get Desmos going. Come on! Come on!
You may put this in the. That's gonna be it?
That's cool. Yeah, so enter this function into Desmos. And then I think I have a sense of what you're gonna see, so let's see if I can do it. First off, I know that there's gonna be this line at 0.6 that we approach as we move out that way. When x is 0, we're at -2. Ooh, those units are not good. That is not a good, so let's see, there's 1, 2, 1, 2, here's 0.6. That's 3/5. We're here, and then, so we cross 0 when x is the square root of 2/3, whatever that is. So something like that. Probably some kind of asymptote here. Is this looking at all like what you're seeing now? Like something like that? So it's,
No?
let me see.
Well, it is.
Yeah, it is. Yeah, you are.
But you.
I mean, it's not done. Yeah, you're right. It does do this, and then it does some stuff like that.
Yeah, it's fine.
But,
You're right,
yeah.
it is the same. No,
It's okay.
That's fair, I see that now.
So what we're trying to do is figure out what is the output approaching as x gets bigger and bigger. And when I look at this, I mean, it might be obvious, but it's only Kellen could do it because he remembered the rule. that it's just the ratio of these leading coefficients in the end. But right now, we're just trying to figure out, what is that dotted line? I'm trying to find how high that asymptote is. Is that, yeah? Cool. Let's try another one. What's this one? And you might want to graph, you know, getting these graphs out, not a problem. Let's see, what is that? 3x squared minus 2. Let's tweak the bottom a little bit and make it 5x cubed plus 3x squared minus 5. Sure. Okay. Yeah.
Don't you still use x squared? Cause
Oh, when you say use x squared, can you explain?
like divide the top and the bottom by x squared.
Yeah, we could totally do that.
Just get
Yeah, let's go ahead and do that.
5x.
I mean, generally, I think what you probably want to do is use the largest exponent
I
that
thought it
you
was,
have.
I thought it was like the common exponent on both the top and the bottom.
I think it's gonna work out no matter what we do. So let's do it your way, because I think that'll work fine.
Okay.
So I'm gonna divide the top and bottom by x squared. So I get 3 minus 2 over x squared, yeah?
Mhm.
And then the bottom, we're gonna get 5x
Plus 3,
plus 3
that's 5x.
minus 5 over x squared, yeah, that's cool.
And then those become 0.
So this goes to 0,
Yeah.
Yeah,
So does
that,
one.
yeah.
this stays at 3,
Mhm.
what happens to that?
That gets
It
big.
gets bigger.
So where does this
To
limit go?
infinity. Sorry,
You wanted to remove it.
So what is the
Oh,
top
that-
approaching? What is the top just approaching?
3.
3.
It's just at 3.
So the top's approaching a fixed thing. What's happening to the bottom? It's blowing up, right?
Going to infinity.
Going to infinity. What's a fixed thing over a giant thing? 0. This is good. We're just practicing. We gotta practice this. You got this.
Is that right though?
That is right.
Oh.
Yeah. Check out the graph.
What happens if you did x cubed, like you said?
X cubed on. Oh yeah. Let's try. Gotcha. I think it works out a little. You don't have to think about this limit, I think is what it is, but let's do it. So if I divide by x cubed, on top I get 3 over x minus 2 over x cubed. The bottom I got 5 plus 3 over x. You know, it's almost like 6 of one, half dozen of the other
Yeah.
kind of thing.
Yeah.
So the top is doing what?
It's
Going to
also-
0, right?
Yeah, going to 0.
And then what's the bottom doing?
Over x. It is also going to 0.
5. This stuff's going to 0. Agreed.
Oh, right.
But we
Like
still
the
have the 5
yeah,
plus,
yeah.
right? So it goes to 5 plus 0, and then that gets us to 0 as
So-
well.
Quick question.
Yes, sir.
Do you only, so, how can I say this? Every fraction that has an x in the bottom, do they all go to 0?
No,
So I think it
'Cause
was-
this one didn't.
Right.
right? This one went to 3/5.
No, I mean like, as in like, a fraction form, like those right there, like it's 3 over x.
Oh, a fixed thing over a power of x. Yeah, that's this rule kind of right
Wait,
here.
but what
Yes,
if it goes?
So no matter if they have
What if the limit's
different
going to
powers,
that's right.
doesn't matter,
Doesn't matter.
okay, cool.
What if the limit's going to 0 though? Because isn't that also?
If I said the limit as x goes to 0,
Yeah.
that's a whole other
But
ball
isn't
of
that-
wax.
Doesn't that still apply to look?
It does. It does. So, but here it wouldn't be a problem. Let's talk about limits just really quick.
Not a good sign.
No, it's fine. So when you get a limit, the very first thing you should try is to plug the limit in.
Yeah, I agree.
You plug and chug is how I always say it. So one, does this make sense? If it does, that's your answer probably. It's true. The only time it's not gonna be is in some weird made up math problem where the limit isn't the same from one side as it is from the other, but in the wild, where you guys are gonna be, this is always your first bet. Just freaking plug the limit in. And if not, if makes sense, yes, done. That's your answer. is it a 0 over 0? So do I have a fraction? And when I plug in the limit, do I get 0 over 0? If that's the case, then I'm gonna L'Hopital it. And so this is what I think you were asking about, Alexander.
Yeah.
But yeah, so I can use L'Hopitals to hopefully get this down. Let's take a look at an example. So, something I actually used when I made a picture just a little bit ago was the fact we're about to prove. So what sign is 0?
Pi.
2 pi?
I'm gonna stop talking now.
I mean, if you're just guessing, yeah. You skew what? 0. There was this man once who told you to memorize some graphs. That man was thinking of moments like this when you would summon them and get some simple values out, right? So this is 0, and then the bottom is certainly 0, because it's freaking 0. So this is L'Hopitalable. This is called an indeterminate form. What's the derivative of the top?
Cosine.
Yes, sir. And what's the derivative of the bottom?
1.
Oh, yeah, nice. What's cosine of 0?
1.
Oh, you didn't even, yes, beautiful. Awesome. So I plug in, now I can plug in and I just get 1 over 1, and the answer is 1. Let's actually talk about what that means, because you've probably done a lot of limits, but you don't really think about what they mean. So when I say this, that the limit is x goes to 0, sine of x over x is 1. What's that?
Go on.
What that means is that when x is small in magnitude, when x is near 0, this quantity is near 1. So let's write that out. So this means that when x, the absolute value of x is small, then sine of x is approximately x. That's what this is telling us, that when you have a tiny x value, the sine of x is approximately the x. You can at least think of this way. You're not going to need a friend on a calculator. Let's make sure your calculator's in radian mode, but I'm going to guess that this is the case. Could someone take the sine of 1,000, please? You should get 1,000 with some change. And what do you actually get? I know what the first ones are going to be, so I'm going to start writing them. But it might be like a 9 here or something. Is it anybody taking the sign of?
I got 0.0009.
Okay, cool. And then some stuff. So round it up, it comes to that. Yeah. So that's a way to think about these limit things. They're not just arbitrary things kind of floating around. And why would you want to use something like this? Let's say you're a physicist studying a pendulum. So I've got a pendulum, and I'm trying to study the motion of the pendulum, especially near equilibrium. And I'm trying to just study what happens if I perturb the system just a little bit. And it's going to pivot there. And let's call theta the angle of rotation off the hinge for the pendulum. But if I develop an equation for this, it's definitely going to involve sine of theta. In fact, I think we get a differential equation, which we will talk about. Actually, that's going to be one of the things we look at. So there's the change of theta, there's the acceleration, the angular acceleration. Plus, then there's some like little number in front of that equals 0. So a physicist might use this equation and go, God, sine is terrible. So you replace sine because you know your oscillations will be tiny. You make the problem simpler by making, the sine goes away. Now we don't have a beastly sine, which is really hard to work with. So we can make life easier by using some of these basic fundamental rules. Here's another one that you may have learned What's that? Can you just do it for me? Let's take a minute.
0.
Oh,
wait, 1.
how are you getting that, PK?
I think 1 minus cosine is still sine, or something like that.
I think you're thinking maybe of this rule.
Isn't it 0?
I think that's right.
Isn't it?
If you plug in 0 for cosine.
What's cosine of 0?
1.
1. So on
Minus
top I
one is
get
0.
0. What is
Over
the bottom
0.
doing?
0.
0.
So it's a 0 over 0 form.
Yeah.
Is this what you were doing in your head?
Yeah.
Okay, cool. So that's L'Hopitalable, right? I don't know what that is. And so what's the derivative at the top?
Minus sine.
Minus side, there we go. Got it, beautiful. This is probably what you were saying, I think. And then the bottom, 1. Now what's the limit? Plug in 0. What's sine of 0?
0.
So 0. I think you said 0 at some point in there. So look, we got some basic things. We're doing the same stuff over and over again. But what does this say? This says that, let's just go on it. I just wanted to do that. Let's get some more stuff done with limits. I think we've got enough basic stuff to at least move on to the next problem. So we came back and we had this problem. And this was infinity. Did we actually show that? Did we actually wrap that problem up?
I don't think so.
No, we didn't. Okay, let's.
I think we just did it as an indefinite integral.
Oh, yeah.
I thought we did, but it's okay. I don't think I summarized it on the board, so let's do that. So given this problem, first thing we did was we replaced the infinity with a number we can work with, a variable. And then we put a limit. We was like, okay, we'll do this and then figure out what that formula does as the b goes to infinity. So we did this, and then we did the antiderivative, and I think Alexander did that for us. And we got natural log of x, and then that went from 1 to b. Yeah.
Yep.
And then we plugged in the limits, so we got limit as b goes to infinity, natural log of b minus natural log of 1. Alexander, again, master of natural log, gave us the 0.
Yeah, natural log 1 is 0.
Exactly, love it. And so we're really just doing this, and then I think we went off on a tangent about what that was, but it's infinity. I think it was something where, yeah, that's where all this nonsense and craziness started. Now we're back.
Yeah.
Now we're back.
We did go out.
So the fact that this integral does not have a finite value, we got a new word. It diverges. So that integral, this is, first off, this is called an improper integral.
So because it's an infinity.
Yeah, exactly. So an improper integral has infinity
Or 0.
as a limit, yeah, or
Oh, no, 0 we can use.
yes, yeah. Hold on, let me just finish what I'm saying here. So infinity as a limit, or infinity is attained, that's the word I'm looking for, is attained inside the integral.
Like you get an infinity out of solving the integral.
What I mean is something like this. So let me give you an example of that. So this was an improper integral. So for this one here, what I mean is something like this. Integral from 0 to 1 of 1 over x squared dx. So notice the limits are finite. There's no infinity here, but when I put 0 in, I get infinity. Does that make sense?
Yeah.
That this blows up. Sketch out the graph if you don't believe me. 1 over x squared looks a lot like 1 over x, an awful lot like it. So what we're doing is we are saying, what is this area here? We can interpret that problem as that area right there. The integral from 0 to 1, and notice there's a big infinite stack that's right at the start of it. These are the integrals we're going to spend today and Friday and probably some of Monday talking about. But some cool things can happen, and in the end, it's just what you've already learned, or what you've already learned about area, what you've already learned about integration, with this limit tacked on. So we have a new final part of the process. Let's take a look at this integral. Speaking of 1 over x squared, now this one's different than what I wrote up there. That one's not the same as this because the limits are different. Let's do this together. Step 1, get rid of infinity because it stresses us out in some way, or it totally gets us very excited, which is what happens to me when I have trouble thinking. And I'm going to actually write this as a power because I want to integrate inside. So leave this to the end. Very last thing here. What's the antiderivative of x to the negative second?
-1/3 x to the
Yeah. Yep. Beautiful.
Mhm.
So it's that, and that goes from 1 to b. Let's plug in the b. So now we got, or plug in the limits, limits period. So I got minus 1 over b, because this is just 1 over x, right? Minus 1 over x. So I plug in the b, and then I plug in the 1, and I got a double negative, so it becomes 1 over 1. So let me stop, make sure that that is working in your brain.
Mhm.
Yeah, good. What happens to this? Oh, yep,
Why is it +1?
because it was minus, when I put in the 1, Jose,
Oh,
because it was minus minus.
yeah.
Does that make sense? Okay, cool. Maybe we can talk while we're here, since we're already chatting.
Sure.
What's this limit?
0.
Solid. So the answer is 1. So check this out. Now look here, this is weird. Because in this first problem, let's sketch it out. So 1 over x looks like this. And there's 1, and it's at 1. So if I have 1 over x, it looks a lot like this. If I have 1 over x squared, it also looks an awful lot like that. So I've got 1 over x squared. It's 1 at 1. And then we know that it decreases to infinity, or to 0 as we move out that way. This area was infinite. That makes sense because it's infinitely big. It's like goes on forever. Our intuition is, of course that's an infinite area. And then we get here and it's like, wait a minute, that's also infinitely big, but it has a beautiful area of 1 unit squared. What the hell is happening? This is weird stuff. So one of the cool things you get to learn in Calc 2, among the many that we're going to encounter, is that just because something is unbounded does not mean it has infinite area. So we can produce things that are infinitely big but have finite interior. Yes, sir?
Oh, I hope this doesn't send us down a rabbit hole.
I hope not, but it's okay. You know I'm all for rabbit holes.
I think I missed the thing on that last problem you did where you had like something that was like this, where it went to infinity, but you bounded off like one section to B, and then like what do you do with the rest? Okay, so here in this problem, it shows that like that area as it goes to infinity is 1 unit squared.
Yes.
Right, but in the previous problem, we like separate, we had.
Well, the limit, and at this point, we had natural log here.
Of 1.
Yeah.
0.
Yeah, this was natural
Oh, so
log
it was
1.
zero.
Yeah.
That's right, I remember that, okay.
Is that making
Yes,
sense?
that's right.
So that went to infinity.
Mhm.
So let's do another one. I'd like you all to help me out on this. What about limit? Nope, that's not what I mean. That's yours. That's for you. 1 to infinity of 1 over the square root of x. Can we just do this? Hey, take a minute. Do this. What do you get? I'll give you full time. I'll eat some snacks or something if I have any. I do. That's good. we're gonna convert it to a power first, right? X to the negative 1/2, just in case something weird happened. Do we have a projector in this room?
Looks like it's just.
Yeah, I guess just that TV, yeah. Oh, what's
You,
that?
you can plug your like device into
Oh,
it, and it
okay.
controls from there.
But I have to bring my own device.
Yes. That would-
There's some kind of keyboard here. I wonder if this, so I wanna get some graphs out so we can look at them. Maybe something can happen here.
Shit, looks like that.
Awful lot of heat coming out of these.
That's exactly what I was thinking about.
What were you thinking
There's
about?
like the screens in that conference gives situation room sort of vibes.
That's exactly
You know,
what I was
the
thinking.
four screens
Yeah.
converging in the middle.
I was thinking about, what's
Okay, I
that?
guess there's,
What's the show Designated Survivor?
I haven't seen.
what show?
Designated Survivor.
Oh, I don't know that show.
Yeah, I know you like Survivor.
I do like
Just
Survivor, yeah. Well, this is garbage. What's that? Want to say that again? But is there oh, wet mics, oh, cool, yeah, yeah, is this what you were saying? Yeah, that's good shit, that's a good observation. Do you mind hooking your, can anybody hook their laptop, up to that thing down there and get us a Desmos? That would be great. We'll see, I mean, it might not even be possible. This glitch on the screen does not look promising.
Over there.
The burnt out spot there.
Into this like, what's that? Like, that's in front
Is
of
it
us.
a HDMI there?
There's like a bunch of cables that go in it.
Oh, can you do that on your iPad? Oh, okay, we've got USB-C there. Nice. Yeah, we'll see.
Stage
Holy shit.
Oh shit, there it is.
Whoa. Good work.
Oh, that's cool.
So good, thank you.
Yeah.
Do you mind if I do, would you bring Desmos up for us?
Sure.
Please. This is fantastic.
I don't know if I can see all the pigment on the monitors.
What's that?
You can see how all the pixels on the monitors.
That's the like, yeah, these are not good. This is very Regis. A very Regis monitor cluster. Cluster is the key. All right, thank you. Let's take a look. Yeah, it's working beautiful. Thank you. Thank you so much. So let's take a look at these curves. And we're going to look at the ones that you're looking at, but I'm going to show you some cool Desmos tech here. So if I take 1 divided by, I'm going to introduce a parameter. So I'm going to make this x to the, whoa, why is there that extra weird, what is that weird? Why do I have an extra? Yeah, I think, yeah, there we go, just 2, there we go, thank you. So I want x to the, now I'm going to introduce a new variable, we'll call it a. Instead of alpha, add a slider, beautiful. And let's come over here. And I guess I could restrict the domain, but we're just mostly interested in this function. So now here's the 1, this is 1 over x, and we're interested in that area. Actually, let me put x equals 1 here so we can, oh, I think I can just enter 1. I saw somebody do that in here just the other day. No, that did not work, so I'll put x equals 1. X equals 1. That was the equals, there it is. All right, cool, that's what I wanted. So the area to the right of that green, I guess I could use the monitors as, there we go, there we go. Oh yeah, look at that, just look in the upper right monitor, perfect, that's exactly what I want. So we're trying to find the area under that red curve, above the x-axis to the right of 1. This is infinite area, as we already showed, because here I have 1 over x. But what happens as I drop, as I increase the, oh, that's not the guy I want to increase. Screw that, we already got the thing up there. So watch what happens as I boost this up. So now, just watch what happens to the curve as, boy, this is not going smoothly here. This is not a smooth thing. Okay, let me fix the range here. I think that's part of the problem. So let's make the bottom range 0.1, and then the upper range, no, make it 5, and we'll have smaller step sizes, so 0.1. There we go. Now it's gonna be a much smoother, there we go, that's what I'm looking for. So here is actually, oh my goodness, yeah, it's like barfing. Yeah.
Just press play.
Why is it, oh, can I
Oh,
use
yeah,
this?
yeah, press play.
Oh, press play, okay.
That would work.
That play also works, yes. So here's 0.1. So note, look at how it drops down as the exponent increases. Now I guess we're just gonna bounce back and forth. So at 1, we're at kind of a critical juncture here. Could you open me a browser, please, really quick? I just wanna find another app. So, I won't look, who knows what's gonna happen, I never want anybody to see what, I don't know, I just wanna Google search. Yeah,
Go for it.
thank you. Cool,
Oh, wait. Yeah, that works.
alright. Cool. So, what I'm gonna search for here is, improper integral calculator, cause there'll be one.
Can you use Wolfram Alpha?
Probably, but I want something live, that it has like, it responds as I change things, and Wolfram's a little static like that.
The best.
Oh, Symbolab, here we go, okay.
Simple Lab's good too.
Symbolab is not bad, yeah. Well, Symbolab is
Yeah, live
looking
experience.
like, yeah, it's looking like garbage right now.
Mm-hmm.
There's Wolfram, maybe this is interactive.
Maybe if you go to the math input version of Wolfram,
What's that?
if you go back to Wolfram, you can like do basic language or math input. I don't know if math input changes it.
Oh, here, it's too complicated. I need something simpler. That's what, here we go. Here we go. All right, so let's put in our function. We can do 1 over x squared. All right, hope it's not as bad as watching like your grandparents do things on the computer. Because sometimes it feels like and I could be your grandparents probably. Not quite, but I'm there.
Not quite there yet.
Yeah. All right, so here's the integral from 1 to infinity of 1 over x squared, and we calculate that. And it gives us 1.0. We did that, right? So now let's tweak the power of x just a little. So now I'm gonna make it 1.1. Getting closer to that 1, that x to the first, 1 over x to the first, but let's see what we got. That is a lie. That is absolutely a lie.
Maybe put,
Put parens,
yeah.
yeah. Which is kind of weird that it needs those, but let's see.
Oh, it's the website.
What a piece of shit. Okay, well, I'm sorry, this isn't your fault. But we can do better by hand.
Okay.
And we're gonna do it way better. So I'm gonna just do the example that I wished we had by hand. Cool, yeah, okay, that's good. Yeah, go away, lousy tech. So let's take a look at this. Integral of 1 over x to the 1 plus, I'll just make a little alpha there, from 1 to infinity, dx. Let's see if we can do that for arbitrary alpha and get a formula. So that no matter what alpha is, we'll have the area right in front of us. So step 1 is convert it. This is probably something I should have showed you at the beginning anyways, and then I got this. Just let me know if anything along the way is looking weird. Does that look okay?
Mm-hmm.
Yeah, the exponents just become negative, right? We're gonna carry this guy along. So now, what's the antiderivative of that?
Huh.
Indeed. current exponent, right? We're gonna add 1. What is
Zero.
that? Close, minus alpha, yeah. So the new exponent, does that make sense?
Yeah.
Okay, cool, so x to the minus alpha, and then I divide by the new exponent, right?
Yeah.
Yeah, and I'm gonna do that from 1 to b. So take a look at that, make sure you're with me. Because now we're gonna put in the b and do this limit. So this is actually x to the, we're gonna assume alpha is a positive number. Because if it's not, this all could, well. Okay, let's just put the b in first, see what happens. So I'm gonna pull the 1 over alpha out front. There we go, that feels better. So this is just b to the negative alpha minus 1 to the negative alpha. Make sure that makes sense, because I kind of did it a little chunky. Is that looking okay?
Yeah.
Yeah? Yeah, PK sounds very confident. Here, okay, thank you. Heads, head nods, yeah. Yeah, okay. Get some other head nods. All right, so now I got this beast right here. Go ahead, yeah.
So how did you?
Oh, this is good.
The parentheses. How did you come up with that?
Putting the,
Oh, I put the b in,
yeah,
Right.
and then I put the 1 in and subtracted. I pulled that 1 over alpha out front, so this is what I actually had to say, this.
Mm-hmm.
And I put the b in,
Yeah.
and then I put the 1 in,
Right.
and then subtracted.
wait, pause, back up. So,
Oh.
look at the middle step, we have the, no, the first step, we find the antiderivative, that's the middle step, yes?
Yes,
And then you plug in b to that.
yes,
Okay, alright.
correct.
Okay,
That's it, yeah,
okay.
good stuff. Good, everybody's riding. I think I might, let's say alpha is positive. If alpha is a positive number, then this is like b to the negative third, which is 1 over b cubed. Does that make sense? That if alpha is a positive number, this is actually just this?
Yeah, I agree.
Okay, cool. So we've got, this is equal to negative, so if alpha is positive, this is what we got. And we still have the limit, gotta do all that shit. What's this simplify to? This piece, this little guy.
One positive alpha,
What's 1 to any power? 1.
oh, yeah.
It's simpler, it's no more alphas. Is that all cool with everybody?
Mm-hmm.
All right, what is this limit?
Which, infinity to alpha over 1.
0.
It is 0, right? We got that rule. I've got 1 over a thing that's blowing up to a power. This goes to 0 because alpha is a positive number.
Wait, can I ask one thing?
Yeah.
You notated, you said, when you have 1 over something that's blowing up to the power, but isn't the power what allows it to blow up?
Yes.
Okay, so they're just together.
Yes, sir.
Okay.
Absolutely. So what do I get out of this?
-1.
I get a -1 on the inside, but I have this guy on the outside.
-1 alpha over alpha.
Yeah. 1 over alpha.
Oh, yeah. I see how we got there, that's not where I was gonna go though.
It's all good, but you follow
No,
it.
I was just gonna do the whole process, I was gonna rewrite the whole thing and then, yeah, it's all good.
You feel good about this?
Yeah.
Do we all feel good about this? Cool, so now check this out. I've got a formula for this problem no matter what it is. So 1 to infinity of 1 over x to the 1.1, which was the damn thing I was trying to do on there. What is alpha here? Look at that, what is my alpha? 0.1. So what is this integral equal to? It's 1 over 0.1. And what's that? We've been doing calculus. Thank you, yes! 10 digits. You guys are doing great on the calculus. I don't know about the division. We're failing, oh, that's just 10, right? Cause that's 1 over a 10.
Mhm.
Yeah, this goes into 1 10 times, thank you, cool. What about this problem? Let's see if we got a rhythm here. 1 over x to the 1.01. What's alpha?
1.01.
0.01.
Oh,
Does that make sense?
Yeah. It's the remainder.
So what is this integral equal to?
1 over x
Oh.
to the 1 times alpha.
It's this, right? We got a formula right down there. So what's that?
Just one.
Kevin doesn't have this many fingers, so we can do it.
100.
Oh,
I think among us, do we have 100 fingers even in this room?
Yeah, we got 10 times 10.
Okay, yeah. So this is 100. Let's do one more.
10 times 10 is that we have more than 100.
Yeah, we
I
got
think
Toby
I've already-
Steve.
Yeah, all right, we gotta get our shoes. I'm the only one with my shoes. Does anybody else have shoes?
We got shoes.
You got shoes. What is this gonna equal?
That's good.
What is that equal?
1,000.
10,000.
1,000.
1,000.
Yeah. See the rhythm here?
Yeah.
How this is going? Notice that the exponent is getting closer to this exponent. Can you guys see down there? Yusuke, is that okay? I know it's a
Yeah.
little rough. So we're getting closer to this problem, right? We're approaching this problem from above. And notice that the closer this exponent gets to 1, the bigger this output gets. So if I had said to you, hey, I've got 1 over x to the 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 1, that's gonna be a big ass number, right? In fact, it's gonna be a 1. It's actually gonna be this number written backwards with an extra 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what's happening here is this. We've got this function. This is 1 over x to the 1 plus alpha. As alpha shrinks, this curve is actually rising up just a little bit. Rising up just a little bit. So as alpha becomes smaller and smaller, this curve is rising up. And what's happening is the area underneath is increasing. But it's always finite as long as this exponent is just a hair over 1. And I'm gonna write this up in kind of a rule that, you know how you guys always have those sheets out that I tell you to have out to reference?
Yeah.
Here's another thing you cannot reference on your sheet that you never reference. Well, let's put it out, we'll pretend. If Dr. T was making a sheet, he would make this note, that 1 to infinity, the integral of that, when I have 1 over x to the p, is going to be finite if p is bigger than 1. And the fancy word for that is it converges. In fact, it converges to 1 over p minus 1. So that means its value is 1 over p minus 1. And it's just the reciprocal kind of what we've done over there. Here I had p plus 1 over there. And here I just have 1 less. So this integral is infinite if p equals 1. It diverges if p equals 1. What happens when I'm less than 1? Let's do that. So when this number here, this alpha, is less than 0, so imagine it's a negative, so it's 1 minus something. Follow this all through. Still all the same computations, except to this point right here. So alpha's a negative number. Imagine alpha's like -3.
Yeah.
So now I have b to the negative of a negative, which is what? Yeah, positive. So I have b to a positive. What happens to this limit as b goes to infinity? So you have,
It's gonna be big.
yes, it just keeps getting bigger and bigger. So when alpha is negative, this goes to infinity, and this integral diverges.
So is the other one too, I'm saying?
Say that again?
The other part, one minus.
Yes, yeah. And then we can't even like do a sum because it just becomes infinite. So this same curve, it's this 1 over x is the important line. 1 over x, if I'm above that, like 1 over square root of x, the area does not become finite. The minute I drop a hair under 1 over x, which is like x, 1 over x squared on this side, the area becomes finite. So let me put this up in a, here's the rule you want. Sorry, let's do it again, all in one fell swoop. If I have 1 over x to the p, dx, this is equal to, we only have two cases. This is equal to 1 over p minus 1 if p is bigger than 1. It is equal to nothing otherwise. That's a rule you're gonna wanna know. And it's up, yeah,
So
so
wait,
Yeah.
but that, so it's the same thing.
yes, I just rewrote it into a compact. You're absolutely right, Alexander. Yeah, absolutely. That's just a good summary of it in a nice way. So when I give you this integral, what's the answer? What's the p?
Negative 1/3,
Uh,
2/3.
look, so check out the form. You're thinking right, but it's the p is, we're assuming it's on the exponent on the denominator. So what is the exponent
Oh,
there?
there's a negative 3?
So
I don't understand what you're, the exponent on the denominator.
what is that? What is x?
Oh,
1 over 3.
1 over 3. Yes. So p is a third here.
You're not moving it up.
Oh.
But look
Yeah.
You see? That's good. So p is a third. What happens? What is this integral? Divergent. Because I know that. This is super, super important to understand roughly this fact. At least to know it. Or have it written on a sheet that you keep in your binder and never look at. That's good too. All right, I'll stop harassing you guys. We're gonna put this up. We're gonna do a little bit more on Friday. No problems on this yet. Yes, sir.
So you say, we should probably write that down, the bottom part?
Yeah, you should probably write that down. Yeah, I am saying that. All right, so Math Amped Club is being run by Dr. Gray today. He's gonna have us build Arduino circuits. I don't know anything about that, but it sounds awesome. I'm super stoked. I don't know anything about it. So Dr. Gray's running it. There'll be snacks, electronics, Dr. Gray. If that's not enough, I don't know what is. So it's in Science 130, the physics lab, at 3:30. And I'm gonna